Introducing the world's first Llama 36B. This is a new model I created using a technique called downcycling. I described this technique in great detail in my previous video. It allows us, individual researchers and small teams, to create highly capable large language models with as little as a few $100s to thousands of dollars. So let me show you how. We finally have the world's first Llama 36B. This one in particular is the pre-trained version of the model that we created in the previous video, part 1. Check it out if you haven't already. Today, I'm super excited to show you this pre-trained version of that model and show you the benchmark results as well as how we got here. So the entire workflow and how much it cost to build this model. Welcome to part 2 of Coding Llama 3 from Scratch video series. Before we get started, please like, subscribe, and turn on your notifications so that you can be notified of future videos. So let's start with the experiment part. Here's an overview of the experiment, and as we go down, I will detail every single step and show you in depth what I actually did here. So the model was Llama 36B. The idea was to create a very strong base model out of the initial downcycled model. And to do that, we needed to continuously pre-train this model on some data. So in terms of data set, I looked online and found out that Hugging Face has a really great data set called FineWeb. It has around 15 trillion tokens. And for this particular experiment, we only needed 1 billion. And I'll show you the entire process of curation and what I did there. In terms of context, I wanted to keep the original 8K context that comes with Llama 3 out of the box. This way, developers can easily work on fine-tunes without having to worry too much about a very small context. 8K is more than enough for majority of the use cases. And additionally, later in the series, we will be working with Infinity Attention and trying to integrate this into this model and other models we will create, which will give us a context of 1 million plus. Regarding the approach, I wanted to do a full fine-tune. But because of tight resources, I had to resort to a QLoRA. Here, the caveat is that full fine-tune, especially in the case of continuous pre-training and if you want to enhance reasoning of the model, is superior to LoRa or QLoRA approaches. It turns out that QLoRA, and this was actually detailed in a recent paper, is not as good when it comes to learning new information. And in this case, we want the model to be able to heal properly and learn a little bit more so that it can perform better or similar to the base model, which is Llama 3 8B. So we did a QLoRA with a rank of 128 and an alpha of 128 as well. And the QLoRA was applied on all linear layers. This is because we want the model to learn as much as possible. Even though it's not comparable to what you would get with full fine-tune, it's still good enough, I believe. So we ran a couple of experiments, and the longest one, which was the main experiment, we ran for 2 epochs. And these 2 epochs were over 1 billion tokens of Hugging Face's FineWeb. The learning rate was 2e neg 4, and the scheduler was a cosine scheduler. So we wanted the learning rate to be adjusted as we trained the model. And the optimizer was Paged Adam W. This optimizer is really good if you don't want to run into out of memory issues. This optimizer is very good for that. And in terms of warm-up steps, we gave it 100 warm-up steps. In terms of costs, this entire experiment cost around $792, out of which 771 went to compute. So in terms of extracting the data set, processing the data, and running some other smaller experiments before we committed into a longer run, that's how much it cost. And the actual long run that created Llama 36B version 0.1, that one cost $532. And of course, we have additionally some storage costs, which is just $20. And the platform I used is Jarvis Labs. When it comes to the data, as I mentioned earlier, we are using Fineweb here, and the particular data slice that was taken from Fineweb was the one from February and March of 2024. This data slice has around 432 gigabytes and precisely 157 billion tokens, out of which we only needed a billion. So what I did, I extracted 8 billion, 6 billion, and then 1 billion tokens out of that data set. But I only used 1 billion tokens for the training. The reason why I extracted those different data slices was because I would actually later on would like to run an experiment with a 1-to-1 ratio. So we have a 6 billion parameter model and we have 6 billion tokens. So a billion tokens per billion parameters of the model. I would like to see if that actually provides better performance compared to the 1 billion tokens. But that's an experiment that will come later on, and I'll detail it here as well. In terms of hardware and time, it took about 10 hours to extract those 14 billion tokens. I think the first 3 hours was me trying an approach that ended up downloading the entire data set to the machine, and then I couldn't load it, so I had to try it again. That's why it took a bit longer. If you are doing this the right way using the notebook I provide you, probably you could slash this time in half or less than half. And then in terms of machine, I couldn't find a machine with enough RAM to process this data set. So I had to rent out a machine with GPUs. And in this case were 7 A6000 GPUs. That gave me close to 300 gigabytes of RAM, which was more than enough to pass through the hundreds of billions of tokens. Now, in terms of the actual experiment that I ran or experiments I ran, we can go here in great detail. So this was the first experiment where I only ran for 1,000 steps. I just wanted to see if the model would perform well and also be able to adjust the parameters to see if we can get better performance. And here we could see that the model actually started to learn, and when it got here, it kind of plateaued a bit. So this was interesting. This was the moment I realized that potentially with more data, we could have better performance, because the model, after this 1,000 steps, started to produce some sensible information. And you could also see that the eval loss is going down over time, which also means that it's good. And it's not overfitting or underfitting, because you can see that the metrics are pretty close in terms of training loss and eval loss. Then I ran a second experiment. This was V1 for a bit longer than the previous one. And I adjusted things like gradient accumulation, batch size, and also adjusted the rank and the alpha of the LoRa or QLoRA in this case. So you can see that V1 now performs better than V0 and is more stable than V0. So that was another big insight that's saying, okay, we could actually have a bit better performance if we tweak these parameters. So after this, I kept on experimenting, but the model only got worse. The more I tweaked the learning rate, the gradient accumulation steps, and QLoRA parameters, it just really didn't outperform V1. So I took all the parameters of V1 and created a longer run, which was the run that took 4 days, and it ran for 2 epochs on 1 billion tokens. And here we can see how that run looks like. So this is V2. V2 performs better than V1, and as you can see, as the epochs progressed, it was actually tending closer to 2, which was pretty good. It was better than anything before, and also here the eval was continuously dropping over time, which was also another good sign. This run took 4 days, 16 hours, and 53 minutes, and I used 4 RTX 6000s ADA. This was enough to run the model without any issues of out of memory, so I was pretty happy with this. And the cost, as you saw earlier, was around $530. Now let's look at some benchmarks to see if the model got better or worse. But before that, I would like to also mention that out of the V2 run, I took some checkpoints that you can also use as a starting point for your fine tunes. So it's not only just the last checkpoint, I took some intermediate checkpoints that are available on my page on Hugging Face. So here are the benchmarks. Let's compare first the best run, so the best checkpoint out of V2 with Llama 3 8B, so that we can compare them and see how far apart are they in terms of performance and potentially what we could do to improve it. So let's start with ARC. Here we can see that our Llama 3 6B is superior to Llama 3 8B. That is a really good indication that the model trained well and it has some reasoning capabilities, because ARC is kind of a collection of multiple choice question answering, and it kind of tests the model in terms of reasoning capability. Then we have HelloSwag, where Llama 3 is superior. Then we have MMLU. This is another reasoning benchmark where Llama 3 8B is superior, but it's not by a lot. Here we are talking about just 10 points, 10, 11 points. And I think with more diverse data set, we could actually close that gap. And it's one of the things I thought. So for our training, I only used English data, so I didn't include any math data set or coding data set. It was just plain old English. And I think that did improve the performance of the model, but it didn't really contribute to the reasoning aspect of the model. And this is something that I want to work on next. Then we have Truthful QA. This is a data set that measures the propensity of the model to tell lies. And here, Llama 3 6B is neck and neck with Llama 3 8B, which is pretty good. For a model that's like 1.3 times smaller, that's pretty good. Then we have Vino Grande. Here we don't have a big gap. We're just talking about a few points, like 5 to 6 points. It's something that we can work on. Here, I'm not super happy with our GSM Q8 score. This particular benchmark measures the model's capability across different tasks. We are talking about 57 tasks. But looking at it, I think with more data and more compute, especially mathematical reasoning data and coding data, we can actually match, if not surpass, the base model's performance. So that's something I'll be working on for version 0.2. So now let's move into a larger comparison where we are comparing our untrained Llama 6B that was downcycled from Llama 3 8B. And then we are comparing that with our trained model against the base model. Here we can see that our version 0.1, the trained version, improved across the board compared to the model that was not trained. When it comes to ARC, HelloSwag, the only confusing ones here are the Truthful QA and MMLU score. I don't know how the untrained model performed better here. That is something to investigate deeper. But when it comes, for example, to Vino Grande, you can see that it was a step up, and especially in the reasoning benchmark, there was a really huge step up here from like nearly 0 to close to 30. So our training had positive effect, which is good. Let's see in 0.2 how much better we can get from this base model. So now let's move into a much broader comparison so that we can see where we sit in the benchmark rank. And here we can see that Llama 3 8B is kind of the best right now. It matches and sometimes even outperforms Llama 2 13B, which is a model twice its size. And here we can also see Yi 1.56B. This is a model that was recently released. And here's our model. Our model doesn't actually lag that much behind. When it comes to ARC, it actually outperforms all of the models here. When it comes to HelloSwag, it's the lowest, but it's not bad. It's just by a margin of around 10 points. When it comes to HelloSwag, it matches Llama 13B, Llama 2 13B, which is pretty awesome, but loses to the other models. When it comes to truthful QA, it matches all of them and actually is superior to Llama 2 13B. And when it comes to Vino Grande, like HelloSwag, it's within range, and I think we can get better from here with more data and more compute. And when it comes to GSM Q8, it actually makes me feel a bit better that our model, whilst being 2 times smaller, it outperforms Llama 2 13B. Now, that is an achievement. From nearly 0 to outperforming at least Llama 2 13B. This is pretty impressive. And let's see with future versions if we can do even better than that. But overall, we are competitive in our category and we are competitive in the ranks. Now, here are some just benchmark descriptions if you're interested to learn about these different benchmarks and what they mean. I'll add this page here as a PDF into our GitHub repo. So let's move into our GitHub repo. The name of the GitHub repo is Coding LLMs from Scratch. And here you'll go into Llama 3 and then you'll go into part 2. Here we will start with the notebook that was used to extract the 14 billion tokens out of FineWeb. And then we will go into kind of actual comparisons and run the model to see how much better the outputs of our trained model are compared to the untrained downcycled model. So here we are, you're just going to install datasets, Hugging Face Hub, Hugging Face CLI, Hugging Face Transfer, and PyArrow. So once you do that, you are going to load FineWeb, and in particular, you're going to load this data slice here. And you want to also specify that the split is train and use streaming, because if you do not set streaming, it's going to download the entire 400 plus gigabytes into your machine, and you don't want that. Then we are going to just filter that data set by extracting only English text. So once you have that set, we're going to extract around 15 million rows from this data set, which is close to 8 to 10 billion tokens. And after that, we're just going to load those tokens into a pandas data frame. We're going to count the tokens. I'm not going to do that here because it takes a long time to do. So after that, you can save, after you counted the tokens that you extracted, you can save them to a CSV file. This is to avoid out of memory issues because you already have 15 million tokens in memory. So you want to kind of move those away. After you do that, you're going to restart your kernel and load that CSV that you saved to your machine. After that, you're going to push that data set to Hugging Face. So now you already have a slice of 8 billion tokens. Then out of the 8 billion, you can extract around 8.3 million rows. That will give you roughly 6 billion tokens. And after you check those again, just to see if you have the number of tokens correct, you are going to push that data set into Hugging Face. Finally, you can just take 1.5 million rows out of the data set. That will give you roughly 1 billion tokens. And you can then just upload that data set. So now you have 3 data sets with a total of 14 billion tokens. I already have uploaded this into Hugging Face, so you can just download from my copy. But if you want to understand how the process works so that you can do this with other data sets, this is how it works, and you can find it in the FineWeb 10 billion tokens. Now, let's move into the interesting part, which is running the model so that we can actually see if it got better. So here I'm just going to load a couple of functions. The first one is just to count the parameters, and the second one is just to generate text using text streamer. So we already went through this comparison here. So we'll just keep that and come into loading the model directly. So first we're gonna load the untrained downcycled model. This should take only about a minute because I already downloaded this model. This model is just our V0. So now that we have done that, we can load our trained model, which is our V0.1. Okay, so now that we have both models loaded to memory, just to double check that this is the correct model, we're just gonna count the parameters of the model, and you can see here that's like 6 billion parameters, which is good. So there's a simple question, and the reason why I asked this question in particular is because the original downcycled model couldn't answer this correctly. It would say things like guidance van Rossum. It wouldn't really answer correctly, and this has been kind of one of the main questions I've been asking the model throughout training just to see how it actually performed, and if we can recover this information as well. So who created Python? It's a simple question. I'm gonna ask this to the untrained model. It's gonna stream the answer. So we can see here that the model said answered by science and then just only said stack until the end, which is not very sensible. So now let's try with our continuously pre-trained model. Here you can see what is Python used for, what's the difference between Python 2 and Python 3. And it says Python is a programming language created by Guido van Rossum in 1991, which is actually correct. This is pretty awesome. We can see the difference between our base model and our pre-trained model. So now let's ask another question. It should be simple. The Eiffel Tower is located in. Since it's a base model, it's not an instruct model, it will not really answer questions the way you expect it to. So you can just have it, it's a completion model, so you can just have it complete the sentence. So here's the untrained model. It says in Paris, France, which is correct. So then it just blabbed on some non-readable text, and then it says World Cup, Euros, and then it just continues going into this repetition mode. Now let's test our pre-trained model. It's in France. It is one of the most famous landmarks in the world. The Eiffel Tower is a symbol of Paris, France. It's a symbol of love and romance. It's a symbol of French Revolution, but still, it's pretty good. The model is actually performing much better than it was when it was originally downcycled. So a couple of things that we can conclude here, let's go back here, is that pre-training actually helped heal the model from the original downcycling process where we cut off a few of the layers of the model. So now we have a strong base model that we can use for instruction tuning. You can build agents with it and so on and so forth. And it's 1.3 times smaller than Llama 3 8B, which means less resources are used during inference, and it's faster than Llama 3 8B. So this is a process that will enable us in the open source community to build really powerful variants of existing models that are smaller, that consume less resources, and are as capable as their original counterparts. This is something that I'm super excited about, and I cannot wait to build even more capable models. And this is why I have an open request to anyone who has A100s or H100s that would like to sponsor this kind of work that will be open source and will benefit the community as a whole. Precisely, I would like to build a Llama 3 with 22 billion parameters, 35, 45, and 55 billion parameters. I believe such a variety of models will unlock newer use cases for developers, and they could use these base models, these pre-trained base models, to fine tune to their particular use cases, which is going to be even helpful for the entire community. So I'm looking forward to hearing from you, and that's it. Bye-bye.